In the classical estimation, the most popular estimator is the maximum likelihood estimator. It fulfills the desirable properties of consistency and efficiency. However, if the sample sizes are small to moderate, or if the parameter values are closer to the boundary of the parameter space, or if we are dealing with hierarchical models, or if the concept of repeatability of sample is not always possible, then this estimator cannot be calculated. Bayes' theorem offers Bayes' estimation technique, which is an alternative to the classical estimation. The Bayes ideology is inference will be based on posterior distribution. This posterior distribution is proportional to the sampling density of the data times the prior density of the parameter. So, the Bayes perspective involves viewing the parameter as a random variable, which is in contrast to the classical estimation technique where parameter is regarded as fixed. If prior information about the parameter is known to be dispersed, then we can formulate diffuse, non-informative or vague priors which are actually assuming that the prior chosen will be uniform in the range of indifference. However, if we have some compact information in a particular region of the parameter space, then it is said to be an informative prior, where we have concentrated probabilities in a specified region of the parameter space. Conjugate priors have the mathematical facility that they lead to posteriors which are of the same model form. So this saves our work on determining the normalizing constant, and it simply requires updation of the parameters. However, we should not use conjugate priors at the cost of diminishing the precisions. So, a careful examination is needed before selecting our priors. In the reliability models, I'll take up two kinds of data: discrete data and continuous data. So, first we begin with the success data, which is the first form of discrete data model of reliability. Binomial distribution will be considered for a fixed number of tested components, where the test will be assumed to be conditionally independent with the given fixed success probability beta. So failure time data is the most commonly encountered data, where x will represent the number of failures before time t. Therefore, PMF of the binomial will represent the number of failures before time t, success. Success is the number of observed failures. Out of n components on tests. Thus, this expression is viewed as a function of p for observed number of successes if x is known, and then it can be labeled as a likelihood function for the binomial data. For n binomial data sets, we will have x1, x2, xn success correspondingly recorded out of n1, n2, nn tests. Then under conditional independence and constant success of probability assumption, the likelihood will consist of product of m individual likelihoods. Conjugate prior is one which has same form as the posterior distribution, and beta distribution will be a natural choice for proportion as a prior candidate because support of beta distribution is on the interval 0, 1. So conjugate beta prior will be considered for the binomial distribution failure data. The form of beta distribution specified where the proportion of success, which is the number of failures, that will be recorded as a random variable. Now, if we combine expression 1 with expression 2, which is prior times likelihood, this is prior, this is likelihood, prior times likelihood will give us the posterior which means the posterior is also following beta, and the parameters are simply updated in the sense that alpha in the prior is replaced by alpha plus x, and beta in the prior is replaced by beta plus n minus x, which means the number of successes are being added to alpha so that alpha can be regarded as a prior number of successful component test, and number of failures are added to the second parameter beta so that beta can be regarded as the prior number of failed component tests, such that the prior sample size becomes alpha plus p. We illustrate this particular with emergency diesel generator data, a very popular data set. This has been dealt in detail by Marx in 1996, publication of JASA. The data refers to the period of 1988 to 1991. In this, there are several diesel generator sets from different plants. So these plants are labeled as plant number 1, 2, 10, 15. So here in this particular illustration today, we take plant number 63 as our data set. It has recorded 212 successful starts, and the demands on the emergency diesel generator is 212. And for the prior distribution, we take plant number 62, which has recorded 273 successful starts with 278 demands on EDG. We regard this plant as the prior source, and we postulate our prior as 10% of the plant 62's sample size. So, posterior for plant 63 will be beta alpha plus x, beta plus n minus x. Now, for the calculation of likelihood, we have 212 success and 0 failures. And since we are considering 10% of success from plant 62 as our prior parameter, therefore, our first parameter becomes 27.3 alpha. And our second parameter, it becomes 10% of the full minus this. Right. So this is the failures. in the prior sample. Therefore, the updated beta will be because of no failures here. So we are 0. So this comes out to be, and we realize here that the posterior distribution is more peaked than the prior distribution, which are of the both of the form beta. So this is how conjugacy helps quickly through updation, and it keeps the matter simple. Even if we do not have very large data sets, we are in the position of commenting on the analyzed data. Now, second type of data in the discrete data models for the failure time distributions is the failure count data. We just observe the number of times when a component fails in a specified time period. Now, after the component fails, we can either repair the component immediately, or and after repair we can put it back in operation, or we can just replace it immediately with a similar component. So Poisson distribution is appropriate for rare events. That means when the failure is not very rampant, right? So we will be testing a component because we know that failure is not at every second or every minute. So it's a kind of a data, it's kind of a component we can rely on. But how much? How much can we rely on this? So we need a model. So let us say if we choose a Poisson distribution to model the failure counts, a discrete event, then we must look at the restriction that the Poisson imposes. The probability of events occurring in disjoint time is independent first, and second is probability of joint occurrence of two events in a short span of time is small. So we are looking at stationarity, and we are looking at the probability of only one occurrence in a small short span of time. So probability of two or more occurrence in a small time event is not allowed. So the corresponding PMF where the observed number of failures y will be anything from 0, non-negative number, and the mean number of failures per unit of time, lambda, should be greater than 0. But for repairable components, lambda will be termed as intensity, not mean number of failures per unit time. It will be looked at as intensity in case of repairable components. T will represent length of the specified time period in which we are observing the events. So we must also, in addition to the two restrictions, we must also, of the Poisson distribution, we must also take care of the fact that a huge restriction in using Poisson model is that its mean and variance are equal. So the mean number of failure per unit time, which is lambda, becomes the unknown model parameter for us today, which we want to estimate. Now, when I view this expression 3 as a function of lambda, given the observed failure counts on the y's, observed failure counts are known, then this expression 3 will represent the likelihood function for the failure count data. So if there are, say, n failure counts in time periods of length, say, t1, t2, tn, Then under conditional independence and constant lambda, likelihood function will consist of the product of the individual likelihood functions of these 1 to n components, each specified by expression 3. Now here we specify the gamma prior as a distribution for the lambda. Now gamma prior is chosen because it also has a positive support. But we know that gamma prior is a conjugate prior. How? Because it will lead to the same posterior. It will lead to a gamma posterior. So we begin. The likelihood follows a Poisson distribution where we have n observed failure counts and we choose a gamma prior, and we know the posterior will come out to be gamma with updated parameters such that the first parameter is updated by adding the total observed number of failures, and the second parameter is updated by the total observed lifetime. So the interpretation will be that beta is the prior sample size, summation ti is the data sample size, alpha is the prior number of failures, summation yi is the observed number of failures. We are dealing in two entities, the number of failures and the corresponding time in which these failures are observed to occur. So these two entities help us to postulate the model. We will illustrate these conditions by modeling monthly number of failures of supercomputer components. These are shared memory processors, not used so much now, but they were used in the earlier times when we had huge computers. So these are the shared memory processors, and we are modeling the monthly number of failures of SMPs. We consider only the first month of operation. So this month of operation means my sample size is 1. Right? This supercomputer has say 47 components, and all these are identical components. So we will have to record failure times of all the 47 components, and we denote monthly number of recorded failures as Y1, Y2, Y47 as applicable in each month. Now, with us considering the first month only, we model the failure count data as where lambda represents the mean monthly number of failures. Now, engineers who work on this, they have some information from their own experience working with similar SMPs, and they expect that there should be no more than 10 failures for each of the component in the first month of operation. So going by this, we can take any prior. Now I wish, going by the interpretation that I have about the parameters here, I wish, keeping the prior consideration in mind, if I take this on 1 month sample, then my prior indications are 5 by 1, right, which is very much less than 10. So later, after we have done this, you can change, and keeping this below 10, choose any combination, and you can change your prior and keep on testing your changes, corresponding changes in the posterior, and how it has implication for the inference. Now, for gamma prior distribution, I am choosing this. If you go for the CDF table, you will see there that lambda, probability that lambda exceeds 10, the CDF table will give me probability of 0.03. So this is one reason. However, as I said, we can always change and try to keep this restriction below 10. Then the posterior in this case, according to our earlier specification, will be based on data. Now, my data is that we have observed 132 monthly number of failures for the 47 SMPs, right? So, the total summation yi for I varies from 1 to 47, we have recorded to be 132. So, my updated posterior will be, say, with a prior of 5-1, the posterior will be, say, 5 plus 132 and 1 plus 47. So, my posterior comes out to be a gamma distribution with parameters this. Using Excel, we can plot the prior 5-1 and the posterior 137.48 on the Excel sheet and see how they look. So, my prior is a little diffused. 5-1. We plot lambda here. So, we have 12 components. Right. So, it's a diffuse kind of a prior, not very peaked in or not very heavy in any particular region. We are plotting gamma densities for 5-1, which is my prior, and which is my posterior 137.48. 137.48 will look a little sharp in the region 2-4. So, we see that the posterior is very peaked. So, what were my data indications? My data indications were like this. This comes out to be around 2.8085 something. My prior indications were like this. Comes out to be 5. Very, very large if you compare the lifetime. And the posterior comes out to be, so we see the data and posterior information are quite close. Prior is not dominating by posterior. So, we can also, when we are experimenting later, then we can treat 9 is the closest to no more than 10. So, if I take a prior where I say that I have a 9 prior instead of 5, then also I will have 9 plus 132 to my updated parameter here, right? So, that will come out to be still 2.937. So, what we infer is that data is providing substantial evidence for a lower mean monthly number of failures than the engineers expected. We have very less cloud in this area, very low number of failures here, right? So, posterior mean monthly number of failures is around this 2.8 something. And posterior, for the gamma distribution, mean of gamma is alpha by beta. We can use that, and standard deviation of gamma is so using this, we can have posterior summaries. This is the posterior mean. We can have posterior standard deviation comes out to be 2438 posterior summaries. Now, if we wish, we can have a credible interval to estimate rather than a point estimate. Some people prefer an interval estimate. In case of Bayesian, we have credible intervals. So, 95% credible interval will be, now the formula remains same, mean plus minus 3 times sigma. But in this case, we will use posterior mean and posterior sigma. So, this is my posterior mean and this is my posterior sigma. So, plus minus 3 sigma, we get 3. 95% credible interval is this many monthly failures. So, this is discrete time discussion on failure time data.